Okay, as promised, here are the last problems, the application problems of this section. Okay, so we are going to use this formula right here, which is the continuous compounding formula. We learned about this in another section. Okay, so the A stands for our amount at the end. Our P is our initial amount, like that big chunk of money that you're going to invest or borrow, times E to the RT. Okay, R is our rate, T is our time. This is, again, is the formula. Anytime you see the word continuous compounding, this is the formula that you'll use. Okay, so it says Laura wants to buy a bond that will mature to $6,000 in 6 years. Okay, so right now we know that the bond is going to mature after 6 years to $6,000. Okay, we know the time is 6. This is our time, 6 years. Okay, how much should she pay for the bond now if it earns an interest rate of 3.5%? Well, our rate, you're going to take that and divide it by 100, which moves that decimal left 2 places. So we're going to use that per year, compounded continuously. Okay, so we want to know how much she should pay for the bond. We're trying to solve for P. Let's fill in everything we know. E, we know our rate is 0.035. And we know our time is 6. I'm just going to write multiplication that way. I don't like to use a dot with decimals. Okay, so guys, right now, this part right here, that is just a number, okay? That is 2.727182, whatever, raised to that power, okay? So you can do this one of two ways. The thing is, we want to get this by itself. Well, this is multiplying. So to solve for a multiplying problem, you just divide. Now, you could write this as a decimal, or you can just divide by that. So I'm going to divide both sides by that e to the 0.035 times 6 power. Again, if you wanted to, you could have used the decimal. Okay, the decimal would have been this right here, 0.035 times 6. You could use that. It's the exact same thing, okay? So I can say 6,000 divided by this here, and she's going to pay that much for the bond. Or you could use this instead of this, which would be 6,000 divided by that decimal number, and notice you get the exact same number. Okay, so we found what P is going to be. So she should pay $4,863.51 for that bond. And then she'd keep it in there for 6 years, and it would be worth that much money. Okay, and you can check this answer. You could plug that right here. You could say this number right here, $4,863.51 times e to the 0.035 times 6. And notice you get 6,000. Okay, got another formula here. Laura places a bottle. Now, from here on out, these problems are going to be solving an equation where our exponent, our variables in our exponent. And this is a new way. We haven't used this way yet. Okay, this is a third way of solving exponential problems. All right, Laura places a water inside a cooler. As the water cools, its temperature C in degrees Celsius. So this here, this whole part right in here is our temperature. Is given by the following function where T is a number of minutes. So that is our time in minutes, since the bottle was placed in the cooler. Okay, I kind of read that broken up, but so they give us this formula. Laura wants to drink the water when it reaches a temperature of 17 degrees Celsius. Okay, so we're going to put that 17 right here. So we have 17 equals the rest of our formula. Okay. It says how many minutes should she leave it in the cooler? So we are going to try to solve for T. Okay, so this is just like any other problem. We've got to get this all by itself first. Well, we have addition, we have multiplication. We are going to take the 7 over to the other side. We're going to do that by subtracting 7. And at that point, this gives us 10 equals, that cancels, we have 15 e to the negative 0.038t. Now we're going to divide by 15 because we've got to get this e to this power all by itself. So we're going to divide by 15. And I don't care if you leave this as 10 over 15 or you reduce it to 2/3. It doesn't matter. I'm going to reduce it to 2/3 just because it's not as many numbers to write. Over here, those cancel and we're left with e to the negative 0.038t. Okay, now what we're going to do is use our cancellation properties. Okay, we learned our cancellation properties in homework 19. I don't know, let me see if I can find one of those. It was on this page right here. We had cancellation, oops, not that page, sorry. It was our first number 20 when I made up that worksheet. Here it is. We learned about cancellation properties with our natural log and with any other log. Okay, this had a power of 1. So what happens, base 19, it cancels out and you just get what your exponent is. Right here, log 30, log base 30, base 30, canceled each other out to get 10. Right here, this has a base of e. This has an exponent of 1. So the e's cancel, so we're left with 1. Right here, this had a log. That's really, you're not supposed to put the e there, but that's, you know, how we know it. That cancels that out, so we're left with negative 12. So knowing that, we now can go to this problem right here. The only way to free up this exponent is to take the natural log of both sides. And the reason we're taking the natural log is it's got a base of e and this is a base e, so they cancel each other out. If we take the natural log of one side, we got to take it of the other. So on this side, we have the natural log of 2/3 equals, it freed up our exponent, negative 0.038t. Now we just solve for t. We're going to divide by negative 0.038. When you do that, this cancels to give us t. And our directions say to the nearest tenth. That's 1 decimal place. So what we're going to do is we're going to take our calculator. We're going to do the natural log of 2/3. Oops, try to do this correctly. Divided by that exponent, or that 0.038. Oops, and that is a negative. Sorry. Let me add in a negative there. Let's see if we can get it so you can see it. Okay. And it's gonna take, it says to the nearest tenth, so 10.7 minutes. Approximately 10.7 minutes for it to cool to 17 degrees Celsius. And I knew it was in minutes because of this and this. Okay. All right. New formula. A radioactive substance decays according to the following function, where y sub 0 is the initial amount present and y is the amount present at the time t days. In this case, it was days. Okay, find the half-life of this substance. Do not round any intermediate computations, round your answer to the nearest tenth. Okay, so find the half-life of this substance. All right, so what we're trying to do is find the time, okay? Now, in this particular case, This y, our initial amount, can be anything you want. Okay, I'm just going to say let's make it 200. Okay, if my initial amount is 200, a half-life means how long does it take to reach half of this mass? So our y is going to be half that, which is 100. Okay, you could have said y sub 0 is, let's say, 30. Its half-life then would be 15. You could use 40 and 20. It doesn't really matter, because here's what's going to happen is we're going to use this formula right here. I'm going to use this 100 and 200, but you would have 100 equals 200 e to the negative 0.062t. And what we're going to do is we're going to divide both sides by 200 because you got to get that e by itself. And this reduces to 1/2. This is why it doesn't matter, because had you used these two, you would have had 15 equals 30 e to that negative 0.062t. Oops, not 300, 30. And you would divide both sides by 30. And notice this is still going to give you that half. Okay, this gives us 1/2 equals that e, because that cancels, e to the negative 0.062t. See how they end up to be the same thing? Same thing if you used 40 and 20. It always, this reduces to 1/2, and this is what it's going to reduce to on that right side. Okay, now that we have this, we've got to free up this exponent. The only way to do that is to take the natural log of both sides. This side gives us a natural log of 1/2. This cancels that out. They both have a base e. So we're left with negative 0.062t. Now we're going to divide both sides by that negative 0.062. And it says to the nearest, round to the nearest tenth. So we're going to say the natural log of 1/2. You could use 0.5 divided by negative 0.062. And this was in days. So the half-life, in order to have half of its mass, is going to be 11.2 days. Okay. All right. Again, when you're trying to find the half-life, you're trying to find the time that the mass divides into, gets cut in half, okay, the initial amount. Okay. All right, so this one right here. Okay, we are back to compounded continuously. So our formula is this. Okay. All right. If 20,000 is going to be invested into an account for 10 years, okay, we know the P is 20,000 because that's our initial amount. That's our P, and they sometimes will call this P sub 0. It really doesn't matter. It's just our initial amount. This is our time, and it says is going to be invested for 10 years to be compounded continuously. Determine the interest rate. So we're trying to find R that would allow the money to double. Okay, well, if our initial amount is 20,000 and we want it to double, we're going to say 20 times 2, which is going to give us 40,000. If it was triple, you'd multiply this by 3. All right, so we know that we want 40,000 at the end. We are trying to find our R, but we know the time is 10 years. So we have R times 10, and I'm going to turn that around in a minute. Okay, so we got to get E by itself, so we're going to divide by 20,000. When you do that, you get 2. Over here, this cancels. So I'm left with E, and instead of having R times T, I'm going to write it as 10 times R. It's the exact same thing. I just like the look of that better. Okay, we got to free up this exponent. To do that, we have a base E, so that means we're going to take our natural log because it has a base E. What I do to one side, I have to do the other. That cancels that out. So I'm left with the natural log of 2 equals, it frees up that exponent of 10R. Now I'm going to divide by 10. And now I'm going to have the natural log of 2 divided by 10. And it says round to the nearest tenth, so that's 1 decimal place. Now, when you see this, you're going to have 0.069. But that's the rate as a decimal. We need it to be a percent because a rate is a percent. Interest rate means a percent. Well, to make that a percent, you move it to the right 2 places. You multiply it by 100. So your rate is actually 6.9%. And it said to the nearest tenth of a percent. Okay. And the last one. The number of bacteria in a certain population increases according to the continuous exponential growth model. Guys, all of these are the exact same formula, except for this sometimes changes, okay? This is going to be P equals P sub 0, our initial amount, E to the RT. It looks just like that one, except for now we're dealing with a population instead of an amount as far as money. Okay, the number of bacteria in a certain population increases with a growth rate of 2.7, so our R is going to be 0.027 per hour. How many hours does it take for the size of the sample to double? Okay, this is similar to the half-life. Again, it doesn't matter what you pick to be P sub 0. P is going to be double that. So let's say we picked P sub 0 to be, oh, I don't care, 400. I'm just making that number up. You could have picked 4. You could have picked 2. It doesn't matter. If it's going to double, you just double this, multiply it by 2, and I get 800. So I get 800 here equals 400 here. That's our initial. E to our rate is 0.027, and we're trying to find our time t. Now, watch what happens. We're going to divide by 400. And we get 2. Just like we did up here, okay? Equals E to the 0.027t. Now again, if you used a number like 10 for our P sub 0, our P would double that, which would be 20. So I'd have 10 here and 20 here. When I divide by that 10, I'm still going to end up with 2. So it doesn't really matter. All right, again, to free up the exponent, I take the natural log. Over on this side, I get the natural log of 2. Over here, these cancel, and it frees up that exponent to give me 0.027t. To solve for t, I'm going to divide by 0.027. And I get the natural log of 2 divided by 0.027. And it says how many hours. It doesn't really say what to round to. So I'm going to say 25.7 hours equals t. If it had said round to the nearest hour, okay, you just say 26 hours. All right. And that finishes up our notes.